Welcome. Today, David Miller, Vice President of ADMET Cheminformatics, will take us on a tour of the new APX.2 software. But before we get started, a few quick housekeeping notes. We take your privacy rights seriously, and by attending this event or participating in the Q&A session, you are allowing us to contact you for follow-up. Immediately following David's presentation, there'll be an opportunity to ask questions. We encourage you to do so, so please submit your answer at any time using the questions panel on your dashboard. And if you need assistance during the webinar, please use the hand raise icon and our staff will immediately assist you. As we all now get settled in, we have a quick question. Which department do you primarily work in? We'll give you just a few seconds to go ahead and submit your answer. And once again, thank you for joining us. And now I will turn things over to Eric Jamois, Director of Business Development. Eric, take it away.
Thank you, Arlene. So good morning, good afternoon, and good evening, everyone. Thank you for joining us for this webinar featuring our most recent release of the ADMET Predictor platform. We're going to focus on the new 10.2 release, which is marketed as APX.2. There are some general enhancements to this release, but many of them are focused on HTPK. So we have hosted several prior webinars detailing the use and deployment of the HTPK technology, and notably the webinar hosted by Roche on April 21st. And you can still find it for replay in the events section of our website. So without any further ado, it's my pleasure to introduce Dr. David Miller, Vice President of ADMET Cheminformatics, R&D at Simulations Plus. David, the floor is yours.
Okay, thanks, Eric. And again, welcome everyone to today's release webinar for ADMET Predictor 10.2. Here is a outline of the webinar. First, I'll provide a brief overview of the ADMET Predictor platform as a whole. Then I will outline some of the more significant new features that we've added for this version. And then finally, I will demonstrate some of those new features using the software. Okay, so the ADMET Predictor is a discovery platform with the four main sets of functionality shown here. The most well-known is property prediction. There are now more than 175 predicted properties in these main categories. Physicochemical includes pKa, log P, solubilities, permeabilities, and so on. Metabolism focuses primarily on cytochrome P450s and UGTs. There are enzyme-specific substrate versus non-substrate and inhibitor versus non-inhibitor models, kinetic models for the 5 major CYPs, and models of overall intrinsic clearance in liver microsomes and hepatocytes. There is also a feature to predict actual metabolite structures. Transporters includes substrate, inhibitor, and KM models for several key transporters flagged by the FDA and other regulatory agencies. Toxicity includes Ames mutagenicity, cardiac toxicity involving HERG, carcinogenicity, and several other endpoints. And finally, we provide a number of customizable risk scores that predict overall ADMET liability as a single number. The predicted properties here are based on machine learning models that we built using training data acquired from collaborations, commercial databases or literature. And our user manual provides details on the data sources, the curation protocols, and model performance. The high throughput pharmacokinetics module provides mechanistic simulations in virtual human or rat species. These are similar to the simulations from our company's well-known Gastro Plus software. This allows estimation of fraction absorbed and bioavailable and a number of important pharmacokinetic parameters. You can generate concentration versus time profiles and estimate the dose required to achieve a target user-specified plasma concentration at steady state. As Eric said, we've made a number of improvements to this module, and I'll go over them in more detail a bit later. Our model building engine allows clients to build machine learning models using their own data, and it's the same engine that we use for our commercial models. Included are our set of over 340 proprietary molecular and atomic descriptors. Both regression and classification models are supported, and the regression predictions come with an uncertainty estimate and classification model predictions with a confidence estimate. And then finally, the Cheminformatics module includes tools useful throughout early discovery in particular, like organizing compounds by common scaffold, R group decomposition, and so on. Among the features for designing new compounds, we recently added a new one called Artificial Intelligence-Driven Drug Design, or AIDD, which is used to discover compounds simultaneously optimized across multiple target objectives chosen by the user. Okay, there are four main options for deploying ADMET Predictor. The command line version runs on both Windows and Linux. It focuses primarily on the ADMET property prediction and pharmacokinetic simulation features, though we are continuing to add new functionality to it. We have clients who have used this command line version to build web services and to power other graphical interfaces, such as Spotfire. ADMET Predictor's property prediction engine can be included as an optional module within our Gastro Plus software to provide estimates of properties for which you do not have experimental data. The ADMET Predictor installer includes both KNIME and Pipeline Pilot components. And then finally, the graphical interface version, which is currently Windows only, that provides a more interactive environment to analyze and explore your chemical data more fully. This is just a brief background on the models underlying our predicted properties. The models utilize our proprietary molecular and atomic descriptors. The atomic descriptors in particular are based on a novel method of estimating quantum level partial atomic charges using a fast empirical approach. The quality of those estimates are illustrated in this plot. We use these descriptors to build a collection or ensemble of neural network models where final predictions are based on the average of the individual predictions within the ensemble. This plot shows the performance predicted versus observed of our PKA model, which is one of several that have ranked #1 in external challenges and third-party comparisons. And our website provides references for several of those. The PKA predictions in particular were the top performing QSAR-based predictions in the Sample 6 PKA challenge. And the results of that were recently published in JCAMD for those who are interested. And the user manual has similar plots for all of our models, as well as a description of the data that we use to build them. The pharmacokinetic predictions are different in that they are not QSAR models, but rather the result of a mechanistic simulation of drug disposition. We model the process using two components. There's the ACAT model to describe the transit through the GI tract and absorption into the enterocytes, and then a compartmental PK model to describe the distribution and elimination. The simulation setup requires input parameters like compound permeability, solubility, intrinsic clearance, etc. These can be experimental values if you have them, or they can be predictions from ADMET Predictor or elsewhere. Then running the simulation involves integrating a system of time-dependent differential equations from which you can extract parameters like fraction absorbed, bioavailable, and so on. This overall process is an only slightly simplified version of what's used in Gastro Plus when you perform a compartmental simulation. This slide shows some performance results for HTPK. As the inputs, we used only predicted properties from ADMET Predictor, and then estimated experimental fraction absorbed and bioavailable in human species using data assembled from the help of these two well-known publications. Unlike with most of our QSAR models, here we judge the performance by the percentage of predictions that fall within either twofold or 1.5-fold of the experimental value. The result percentages are shown here, and they're actually quite reasonable given the complexity of the underlying in vivo processes. Particularly for FB, where we have to predict the first pass metabolism using just the chemical structure. In many cases, the performance can be improved by using whatever experimental properties that you might have as the input parameters. Okay, so that was a very basic overview of ADMET Predictor as a whole. So now I would like to briefly go over some of the new features in version 10.2. Okay, so the most important enhancements in this version were to the HTPK module. These were funded through a collaboration with a large pharmaceutical company partner over a period of more than 18 months. This company is a longtime Gastro Plus user, but wanted a more streamlined PK simulation tool geared toward early discovery that they could roll out to their chemistry teams. So over the course of the collaboration, we've been able to make a number of useful improvements to the overall HTPK functionality. And I'll just summarize those in the next couple of slides. Okay, so there is now support for IV Bolus dosing, complementing the previous option for immediate release tablets. We've extended the dose optimization workflow, and I'm going to talk about this more during the demo. Target plasma concentration can now be an average, a minimum, or maximum, and can be a total concentration, meaning bound plus unbound, or unbound only. We've significantly improved the algorithm for computing the number of doses required to reach steady state, and the workflow can now be run from our MedChem Designer sketch interface, as well as from ADMET Predictor itself. Similar to Gastro Plus, Predictor now provides an estimate of the AUC from 0 to infinity. That's calculated by extrapolating the CP time curve for the first dose interval. I'll talk a bit more about this later. We've added an option to correct the in vitro clearance using a specified % unbound value. Previously, you had just two options, either no correction or an automatic correction using either FU-MIC for microsomes or the Austin equation for hepatocytes. We added two new options to facilitate comparisons with our Gastro Plus software. So you can now turn off the passive renal component of plasma clearance, which we calculate as GFR times fraction unbound. Compartmental simulations in Gastro Plus omit this renal term. And you can choose whether or not to adjust the FUP for non-specific binding to lipids. This setting affects higher log P compounds, and GastroPlus uses the correction by default. CP time profiles can now be generated for up to 16 compounds simultaneously. And there is the option to append a CP time profile to a previously generated one. This is useful for more easily visualizing the effects of a parameter change. And I'll show this later. We've changed the default volume of distribution input to be the mechanistic estimate. And that's based on calculated tissue KP values. Previously, the default was ADMET Predictor's statistical model. Our user manual discusses the differences between those two approaches, and of course, you can choose whichever input is most suitable. And then finally, we've made changes to several of the physiological parameters to make them consistent with the latest version of Gastro Plus, which is 9.81. This slide just shows some of the user interface changes. This is the workflow for dose optimization, which I'll show in a few minutes. So we have options here for the dosage form, for the target plasma concentration, non-specific binding in the in vitro clearance experiment, and then on the advanced dialog, options for the adjusted FUP, for the renal clearance term, and then here for the change in the default volume of distribution parameter. I just want to mention, if you want to change this setting, there's a button here you can click to change it for a given simulation, or you can edit the relevant parameter file called an HIA file in the application folder to make a permanent change to the default setting. Okay, so this slide shows a comparison between HTPK simulation results and those from the latest version of Gastro Plus, 9.81. This was using a set of 200 randomly selected FDA drugs at a dose of 1 milligram in human species. So in Gastro, we ran compartmental simulations using predicted properties from ADMET Predictor as the inputs. Then in Predictor, we had to make a few settings adjustments to ensure consistency with Gastro. So the volume of distribution was switched back from the mechanistic to the statistical model. The adjusted FUP setting was turned on, and the renal clearance term was turned off. So the plots here show the resulting predictions of fraction bioavailable and AUC, and you can see the excellent agreement between Predictor and Gastro. We found that the discrepancies are mainly due to the somewhat simplified model of compound precipitation that's used in Predictor versus Gastro. These discrepancies will be magnified for lower solubilities and larger doses, but they're generally quite minor. Okay, so moving on, we've added several new command line capabilities, including metabolite prediction, solubility or log D versus pH profiles, compound transformations, so that can include things like standardizing compounds, but it's actually more general, and then generating tautomers. These new features are what we call Scriptfile workflows, where ADMET Predictor is invoked using a text file that contains the parameters that control the run. We've extended all of the Scriptfile workflows to support override of parameters on the command line. So as an example here, the structure file parameter in the metabolites script file can be specified on the command line like this. This is convenient because you can leave parameters that you don't usually change defined in the file, like for example, the list of metabolizing enzymes, and then specify the parameters that do change on the command line directly, like the input structure file. Note that we don't yet have a pipeline pilot or NIME components for these features, but that's something that we plan to work on in the future. And I'm going to see if I can demo just a couple of these a little bit later on. We've added a new model of mutagenic risk that we call MUT-X risk to complement the existing one. This was motivated by recent literature and findings from proceedings of an international workshop on genotypic testing. The model has new rules and weights that reflect the importance of the TA98, TA100, and TA1535 strains and the interactions between them. This new model exhibits enhanced sensitivity and specificity on the benchmark Hansen data set. Full details about this model are provided in our user manual. And then finally, several features were made significantly faster by exploiting multi-core CPUs. So among them are searching by substructure, transforming compounds, such as standardizing them, adding compound attributes using equations, queries, and so on, and then generating scaffold classes using a method we call frameworks, which is the Merkos, I think it's Merkos and Bemis scaffolds, or sort of arbitrary scaffolds defined by the user. I'm going to also try to demo a couple of these in a few minutes. Okay, I've left out quite a few enhancements that you can learn about in our README file and in the user manual. But for now, I'm going to stop this and try to demo a few of these features. I think I'm first going to just try to increase the resolution just a bit to make it easier to see. Hopefully this will work. Okay, now I'm going to launch the just released ADMET Predictor X.2, as we call it. Okay, so I want to start by showing some of the improvements that we made to HTPK as part of our collaboration. So I'm going to open up a data set contained in this SD file. It consists of 1,000 FDA-approved drugs. To help give a sense of the relative speed of HTPK, I'll start by predicting all of our ADMET properties. So I'll include all categories, so phys-chem, transporters, and so on, including our molecular and atomic descriptors. Click calculate. You'll see that it's pretty fast. Takes about 5 seconds on this 6-core laptop. And the result is a series of prediction columns. The first are the optional and configurable star plots, which let you see a group of predictions in a single graphical column. So for example, this SIP substrate column shows by the filled wedges which SIP isoforms a compound is predicted to be a substrate for. The individual predictions are displayed in the subsequent columns, You can view them all together like this or in their respective categories, phys chem and so on, using these buttons at the bottom. If I just scroll a little bit further, I just want to reiterate that our classification model predictions by default show the percentage confidence estimate. For the regression models, there is the option to display similar uncertainty estimates. Those are represented as 1 sigma lower and upper bounds. And the user manual has a lot of theory behind those two estimates. And then finally, predicted values are marked in red and they're underlined if they are outside the so-called applicability domain of the model. We say that these predictions are out of scope and should be used with caution. Okay, now I will perform an HTPK simulation. I'm going to use what we call the FA-FB workflow, which runs a single simulation at 1 or more fixed doses. In a little bit, we'll discuss the more complex dose optimization workflow, which generally runs many simulations at different doses in order to find an optimal one. So if I launch that workflow, I'll leave human as the species, immediate release tablet as the dosage form, and a dose of 1 milligram. The other inputs, like the intrinsic clearance here, and those on the advanced tab, like log P, solubility, and so on, these will be ADMET Predictor predictions. As I mentioned, if you have experimental data or your own predictions, you can use those as well. So when I click run, the simulation is also pretty fast. It takes on the order of 5 to 10 seconds for these 1,000 compounds on this machine. And the result is also a series of prediction columns. So fraction absorbed, fraction bioavailable, and the pharmacokinetic parameters. As I mentioned in the slides, one of the new features we added is an estimate of the AUC from 0 to infinity, which is calculated by extrapolating the simulated CP time curve. If I sort on this column, you see that for some compounds, it's not possible to estimate that value. If I just select one of them and predict its CP time profile using the same parameters, you'll see that the Cmax is not quite achieved in the default 24-hour time window. So there's no way to reliably extrapolate this curve. Now, both the clearance and the half-life are defined using this AUC 0 to infinity estimate. Clearance is proportional to dose over AUC, and the half-life to the volume of distribution over this clearance. So both of these are also missing for these compounds. As a quick aside, for those of you who use Gastro Plus, you'll recall that there's a half-life estimate reported on the pharmacokinetics tab that's based on a different clearance value, namely the scaled plasma clearance from the well-stirred model equation. ADMET Predictor does output that clearance value as well, actually 2 of them. This is without and with the renal term added. So in Predictor, you can use an equation to define the same theoretical half-life that's shown in Gastro Plus. For this release, we also added a feature to tell Predictor to compute those kinds of user-defined equations automatically each time an HTPK simulation is run. I previously added that half-life equation to Predictor. So if I activate that auto compute feature, again, we just added this, and then rerun the HTPK simulation, and I'll just do 1 compound this time. you'll see that it adds automatically this new half-life column, and the value here should be the same as the one that you would see in Gastro Plus. Okay, now I want to shift gears a little and discuss the dose optimization workflow. For simplicity, I'm going to use just a single compound, which will be the drug alprazolam. So I'm going to locate that compound using a text search, and then I'll just hide everything else. Just make this a little bit bigger. Okay, so you'll recall that the dose optimization feature is used to estimate the dose required to achieve a target plasma concentration at steady state. You would typically use experimental IC50 values as the target plasma concentration, and then this feature would help you prioritize those compounds predicted to require a low oral dose. Here as an illustration, I will use the simulated plasma concentration as the target, and then verify that the dose optimization feature can recover the dose used in that original simulation. So I'll start by using that CP time workflow to run a single simulation at a fixed dose of 1 milligram. I'll specify that it be dosed every 24 hours for a number of intervals so that steady state can be achieved. We don't know a priori how many doses will be required to reach steady state, but in this example, 3 turns out to be about sufficient. And I'll come back to this point in a little bit. So if I generate the CP time profile for the 1 milligram dose and 3 dose intervals, just run that. You'll see first that the steady state is at least approximately achieved. So the Cmax and the Cmin are not changing appreciably after the second dose. Okay, now the average plasma concentration at steady state is defined as the steady state AUC divided by the dose interval, which is 24 hours. In the legend here, we see the steady state AUC, which is about 47 nanogram hours per milliliter. And you can see that it's actually the same as our estimate of the AUC from 0 to infinity, which we obtained by extrapolating just this first dose out to infinity. So back in Predictor, where we have that AUC 0 to infinity estimate from our previous run, we can calculate the average plasma concentration at steady state using an equation. So I can add an attribute based on an equation. We'll call it C, oops, messed that up. Okay, using an equation, we'll call it C target in nanograms per milliliter, and we'll define it as our estimate of AUC from 0 to infinity divided by our dose interval, which is 24 hours. Okay, and we get an average target plasma concentration of 1.97 nanograms per milliliter. Okay, so now I can run the dose optimization feature. Okay, so you'll see that the interface for this workflow is very similar to the others we've seen, except that it takes as input a target plasma concentration instead of a dose. So I'll specify that we're targeting the average plasma concentration, and for the value, I could either type the 1.97 or select this new attribute that we just added inside Predictor. Now, when we run this optimization, we should get 1 milligram as the optimal dose, since that's what we use to generate this target plasma concentration. So what happens under the hood is that it starts with this default initial dose of 10 milligrams, which will be given every 24 hours until steady state is achieved. And that's determined by Cmin and Cmax no longer changing within a small tolerance. If the resulting average plasma concentration at steady state does not match our specified target concentration, the initial dose is adjusted And the entire process is repeated using that new dose. And then this all continues until a dose is found that gives the desired target plasma concentration, at which point that optimal dose is returned as the answer. So this workflow is significantly more complicated than the FA-FB workflow, and it does require more time. But if I now quickly run it for just this one compound, you see that it's fast. We find that it's generally only slower by a factor of about 4 or 5. So it would take about 20 seconds or so to run for all the 1,000 compounds that I originally had. Okay, so we see that in fact it does find the correct dose of 1 milligram. If I scroll to the right, there's a column here called dose count. So we see that it actually takes 5 doses to reach steady state. This dose count value will generally be different for each compound that you run through the workflow. Okay, I'm going to just quickly scroll back, and then as a last illustration of the feature, I'll just rerun the dose optimization workflow and instead request that our 1.97 nanograms per milliliter be the minimum plasma concentration at steady state. This is one of the new features that we added for this release. So if I rerun that, you'll see I get an optimal dose of 2.9 milligrams instead of the original 1 milligram. So if I take that that dose and I run the CP time curve using 2.9, I'll use still this guess of 3 dose intervals. You'll see first that again, it looks like steady state is at least roughly achieved here. And if I look at the minimum plasma concentration at steady state, you'll see that it is exactly what we were targeting. It's about 1.97 nanograms per milliliter. Okay, so hopefully that has at least helped to illustrate how the dose optimization feature works and given you some ideas of how it might be used. Okay, now I want to show some of the improvements that we've made to the feature for displaying those concentration versus time curves. I'd like to illustrate those using our companion MedChem Designer sketch tool. So I can send just this one compound over to Designer, our sketch tool. Designer has a lot of useful functionality in addition to drawing. You can predict ADMET properties directly within this interface. This is quite useful for experimenting with how a structural change might affect properties. You can also predict metabolites here. The default workflow includes the 5 major CYPs plus aldehyde oxidase. So I run it, it generates a view like this. I think in a few minutes, I'm going to talk a little bit more about metabolite prediction. Designer also incorporates the HTPK functionality, including the CP time profiles. So I'm going to first run a profile here. I'm going to switch back to our 1 milligram dose for 1 dose interval, and I get a curve that looks like this. Now, if I want to compare this with IV bolus dosing, in this release, now you can leave this curve open, rerun the simulation, and now there's a new option here to attach the new curve to a previously generated one, which I can just select. And then now if I, for example, switch this to IV bolus and run, now it's really easy to compare the oral with the IV dose. Just one more example, this time by changing the compound solubility. So I'm going to relaunch, switch that back to tablet, leave this option, and then I'll show the advanced tab. Solubility is here. A few versions ago, we added the feature that if you have previously generated ADMET properties, either here in Designer or in Predictor, you can load them directly into this dialog as numbers. And that makes it quite a bit more convenient for experimenting with a parameter change. So here, let's say I increase solubility by an order of magnitude, as an example. Now, if I run it, you can see the original oral dose and then the oral dose with the higher solubility. This approach of varying the input parameter values is something that we do pretty frequently to estimate the expected bounds on these CP time profiles. So it's useful to be able to plot the multiple curves in just one chart window like this. And then finally, in the slides, I mentioned that we added the ability to process more than one compound at a time. So here in Designer, it's particularly easy to just copy and paste. Just here's an example analog, and then now you can launch that feature with both compounds and just see them side by side. So here's the original, and here's the analog. Again, these enhancements are available both here in Designer as well as in Predictor. Okay, so moving on from HTPK, I want to just briefly show some of the features that we've made faster through parallelization. So I'm going to open up a different, much larger data set. This one contains 25,000 compounds. These are from Kemble. The file format here is XTK. That's the native predictor format. So it opens very quickly, and the file can contain information about the columns, heat maps, chart settings, and so on. The first feature we made faster is the basic substructure searching. So if I launch that feature, I'll just use, I have a kind of a generic Marcouche steroid scaffold here. So again, 25,000 compounds. So it's less than a second to search, and it found just over 700 hits. A related feature is to use a list of queries to add numeric scores to the compounds. So here I'll choose add new attribute to all the rows. This time using a query. I'm going to select a file called reactive metabolites. This is something we distribute with the software. It defines about 40 substructures taken from literature. They are associated with reactive metabolites. And the result of this operation is going to be to assign a score to each compound equal to the number of those substructures that match it. Running the feature is going to require about 40 queries times 25,000 compounds. That's 1 million searches. But now, since it exploits the multiple cores, it runs, very fast. It would be even faster if I weren't streaming over GoToMeeting right now. Okay, I think that's all I wanted to say about that. We've parallelized a few other features for this release, and our plan is to gradually add more of those in subsequent releases. Okay, the last thing I'll just briefly show is a couple of the new command line features that we've added. This is a Cygwin shell on Windows. You can also use DOS. And in the next few weeks, we will be releasing the Linux version of ADMET Predictor 10.2 as well. The first one I'll show is metabolite prediction. As I mentioned in the slides, this uses a script file that we distribute with the software. I'll just quickly show the file in Notepad. So you can see it's just a text editable file. This is just, I highlighted one of the parameters in the file. So it's the list of metabolizing enzymes. By default, it includes the 5 major CYPs plus aldehyde oxidase. So normally you would first edit this file and make any changes that you want, and then invoke your modified script. So to run it, you would type the path to predictor. I have a shortcut for that. Then the name of the script file. And then I mentioned in the slides that now you can override parameters from the file directly on the command line. So if you didn't have your structure file defined in the parameter file, you could specify it like this. It's a little tedious to type. I'm going to use just one compound, but there's actually no limit to the number of compounds that you can run. So it's going to load predictive models and then predict metabolites. The result is going to be the metabolite stored in a new SD file. I'll just quickly display those using the predictor GUI. Okay, so there's a setting in the file that says that the substrate should be included in the output. That's an option. Metabolites listed here, M1, M2, and so on. You have the list of responsible enzymes, predictions of intrinsic clearance for each of those selected enzymes, whether or not the metabolite was produced through an intermediate, information about the relative abundance of the metabolites, and so on. This is the same output that you would get if you ran metabolite prediction directly from the ADMET Predictor interface, and then similar to what we saw earlier in MedChem Designer as well. And then let's see, I have just a couple minutes left. I want to quickly show the other, or one of the other features, which is the solubility versus pH profile. So here, for every compound in the input file, it produces a separate text file with predicted solubilities at multiple pH values between 0 and 14. So to run that one, similar, there's a different text file for that. And again, I'll give it the one compound, although again, there's no limit to the number. Loads models, it's going to generate the profile. Here, there's a new text file. I'll just quickly show that in Excel, just so we can see the plot. So you get two columns of numbers, the pHs and the solubilities. So I can just show that really fast here. So this is the same plot that you would get if you were to run that equivalent feature from within the ADMET Predictor interface. Okay, so I think that was 2 of the 5 new command line workflows that we added for this release, and we plan to gradually add more of those in future releases. Okay, I think in the interest of time, I will stop here. I want to thank everyone again for attending this webinar. I hope you found it useful.